So today we are hosting Katie Parnell from University of Southampton. Dr. Katie Parnell is a senior researcher fellow in human factors engineering from the Transportation Research Group at the University of Southampton. She has been a member of the REASON project team since the start of the project, focusing her research on resilience of future automated transport systems. Katie has also been involved in other task projects looking at the trustworthy swarming drones. She has recently been awarded an anniversary fellowship from the University of Southampton to study gender equity in future transportation systems and has a particular interest in socio-technical systems as well as user-centered design. So please, Katie, whenever you are ready, we can start.
Great. Thank you, Sinem. So my title of the talk today is Human Factors Approach to Resilience in Automated Systems. And essentially it's just an overview of the work that's been done on the REASON project over the last couple of years, sort of quite a brief run through of those few years and the work that we've done from our kind of human factors perspective and how we've been working with some other people in the University of York as well. But it's work I've done in collaboration with my colleagues on the project, Siobhan Merriman and Katie Plant, who is the co-I of the REASON project as well. So just to acknowledge them, there's a sort of shared output. So I'll just give you a little bit of an overview of this talk I'm giving today. So I'll start with a bit of background to human factors engineering, what we do at the University of Southampton, and sort of what human factors is. If you're not familiar, I'll then talk through the work that we've been doing on our transport scenario as part of the REASON project. So some resilience modelling work, a paper that we published looking at sort of task modelling of resilience from a human factors approach, as well as cognitive work analysis and strategy analysis, which is sort of two key methods that we've applied to this transport scenario. I'll then go on to the work that we've applied to the dressing scenario, so with an assistive dressing robot, which is sort of an application of those other modelling work to the dressing scenario, which is a paper that we are going to be presenting at the TAS Symposium. It's just been accepted, so there'll be sort of an early preview of that results and the sort of work that we've been doing there. And then I'll finish with some future work. So just to give a brief overview of human factors engineering and how we frame it at the University of Southampton. We're looking at human, how they interact with other people, other technologies, and also their environment. And we look at it sort of from a socio-technical systems perspective. So we have the social system, so we have the people, but also their cognitive capacities and their social interactions. And we take a lot of work from the psychology discipline. A lot of us have sort of psychology backgrounds. So we like to look at this sort of the people in terms of the sort of broader interactions from a psychology perspective, but also the wider structure of the organizations that they function within. And then we also look at the technical system, which is that more engineering based element of human factors, which is the physical system. So that's where the automation comes in relation to this work, but it's sort of the hardware, the software, also the facilities. And then we also have the tasks that are sort of completed with these physical systems. So what's actually been done, what are the interactions with them? And then we look at those interactions between that social system and the technical system together. And importantly, we look at that within the sort of wider environment that those interactions are occurring within. So that sort of complex environment. So this is sort of building on that. So again, talking about socio-technical systems, but sort of another representation, but just to show that we look at the individual, sort of that human focused approach, but then we also look at that within sort of relation to the broader team that they might interact within. And that could be a team of people, but also a team with a robot, so human robot teaming or automation teaming. And then also looking at it within the broader system that they operate in as well. So that's looking at sort of society and perhaps the regulation. So we like to look at it in terms of a bottom-up approach, looking at the individual human, but also a top-down perspective and how society is going to sort of look at the interactions and how to sort of manage that from a top-down perspective as well. And then just lastly, a lot of the work that we do is all very user-centered, and we like to engage with users throughout all of our work, bringing them into the design of systems, sort of future systems, automated systems, as well as looking at how we can integrate them in the development of potential training programs. It's another side of human factors, and also regulations of systems and things like that. So in all the work that we've done, it's always trying to incorporate users throughout. So that's just a broad overview. Another sort of key element that human factors looks at is sort of making the difference between these, sort of highlighting differences between work as imagined versus work as done. And work is anything, sort of can be the interaction between a human and a robot. It can be what an automated system is doing, but we just sort of frame work as the system that we're reviewing. So there's often work as imagined when we're designing systems, how we imagine it might look. And then work is disclosed, so what we're saying it's going to do. But this can be different to sort of how work is prescribed and also how work is done, and which is kind of the key area that we're kind of looking at. So how is work actually done in a system, or may be done, versus how is it imagined to be done? And quite often these things are quite different. So we try to sort of look at this in terms of making sure that systems are designed so that things are done how we want them to be done, how they're imagined to be done, and they don't get this sort of discourse. So we've been focusing within the Reason project on the transport scenario, so looking at resilience in future automated transport systems. And so we've got a transport scenario that we've developed and we've been working on, which is looking at the interaction between vehicles and vulnerable road users. So obviously in future transport systems, there's going to be more automation on our roadways, but also with the sort of drive towards more sustainability targets, there's also going to be more active travellers, cyclists. There's also sort of a big upsurge in the number of e-micromobility, e-scooters, e-bikes and things like that on the roads as well. So we've been sort of forward thinking and looking at how the interactions between these two different types of transport modes might be interacting in the future, and sort of identifying that at the moment they're not really that compatible. There's quite a lot of conflict between drivers and cyclists potentially on the roads at the moment. So we've been looking at this shared roadway scenario where the cyclists and the drivers have to share the roadway, and often just a cycleway that's sort of implanted on top of a roadway that's not really been well integrated or well thought about. So we've been looking at this initially as a baseline on how drivers interact at the moment. So this is a scenario where the vehicle in red has got to overtake the cyclist on this shared roadway. So they've got to wait for the vehicles from the other direction, the oncoming traffic, to be clear, so that they've got enough space to effectively move out into the middle of the road and then overtake the cyclist and carry on with their journey. And we've been looking initially at just sort of the next levels of automation, which are currently being integrated or are soon going to be coming to our roadways, where there's still some sort of interaction between the human and the driver and the vehicle. It's not a fully automated level 5 where there's no inputs needed. We've been looking at it from these sort of level 3s and level 4s of vehicle information, because it's kind of the most interesting from a human factors perspective, and also where there's going to be most potential for some issues. And again, just coming back to this, so we've been looking at it as sort of the baseline of what's currently been done, how drivers are currently interacting with cyclists on the road, and then looking at how we can then integrate automation effectively, rather than taking this, how we imagine a future automated system to look. We've been saying, okay, what's the baseline now, and how can we integrate automation effectively to make sure it's sort of being resilient and sort of is actually useful in the future. So we built up this sort of methodology for resilient automation requirements, and this is work that's been published in Applied Ergonomics last year, and it's got a number of stages, and there's a number of different methods that we've applied, which are current and very popular human factors methods, but what we've done is sort of apply them in combination, which is the sort of novelty of this approach, and applying them to sort of resilience. So the first stage is the scenario definition, which I just talked about that transportation scenario. And then sort of the first objective within that is to identify all the tasks and all the actors involved with that. So who does what? And we've been doing that from that current non-automated approach to understand who's doing what currently. The second phase is then to identify what can go wrong. So from a resilience point of view, where is there possibility for things to go wrong, for errors and failures to occur? So we've got a popular human factors, human error methodology applied to that. And then the third stage is how can we improve it? And this is where we identify automated solutions to build upon the current transport system and identify where automation can overcome some of the limitations of our current systems and be integrated effectively. And then we go through that process again. So just to sort of go through that in a little bit more detail. So the first stage, we've got two methods. There's the hierarchical task analysis, and then operator event sequence diagrams. So hierarchical task analysis is kind of the foundation to all our human factors work. Well, most methodologies sort of start with this as sort of a start point, and it's really useful at just sort of understanding what goes into a certain task, and what are the kind of goals, and breaking it down into sort of minute details, which can allow us to analyze it in a bit more depth. So we had this task analysis that was actually already done from a previous project that Katie led, which is the critical project looking at interactions between cyclists and drivers and developing a training program. And they did this hierarchical task analysis that started off with safely overtaking a cyclist and broke that down into 7 sort of goals related to this. So detecting the cyclist, reducing the speed. And then each one of these 7 goals had a further task related to that. So the task of just assessing external environment, that had 9 further tasks, and each one of these had individual tasks related to it as well. So you can see that we go down into sort of breaking a task down into its sort of step by step. And then they identified from this, they did work with professional cyclists and road safety experts going out onto the road and sort of validating this, and they identified 66 tasks under these sort of 7 goals. So it does become quite complex when you start to break it down. And so we then went on to identify, okay, if these are the tasks, what are the different actors that are acting to complete these different tasks? And this is when we did the operator event sequence diagrams. So these are really good to sort of map out the relationships between different actors in a scenario, and trying to explore what those interactions might look like. And importantly, they're really good at looking at how interactions might then look like when you start to add automation in, how they might change. So you can see at the bottom here, we've got different, so we call them swim lanes, but every actor has its own swim lane. So there's one for the vehicle, the driver, which we've broken down here into the different senses. So what they're hearing, the auditory, the physical, the cognitive, and the vision. Then there's the road infrastructure. And then there's the cyclist as well with their different sensors as well. So there's a different swim lane for each of those different actors. And then we can map on the task to see how those different actors relate to the task that's being completed. So it's another visualization of sort of breaking things down a bit more. And so it looks a bit like this, but she can't see, but I'll go through in a bit more detail. And the other thing that we did here was sort of map on some of the resilience cornerstones. So our literature review sort of identified these resilience cornerstones, which were published by Holmegol. And he identified 4 key sort of cornerstones or key aspects of resilience, which was monitoring the system, anticipating possible threats, responding to critical events, and then learning from them to prevent them from happening again. And then when we were sort of looking at this in relation to automation and sort of future resilience, we identified that there might be a corner which is detecting. You need to be able to detect a system, particularly when you're working with automated systems. Detection is really important. So we've added that in here. And so just to sort of illustrate this, with the scenario, so we've got this initial monitoring phase where the vehicle is sort of monitoring the roadway. There's some road infrastructure that signs that there's a bike lane, and the potential for cyclists to be around, so the driver's aware of that. So they're monitoring. The cyclist is also aware of might be cars coming up from behind them, so they're monitoring the roadway as well. And then they've got this detection phase, which is the phase in which the cyclist is spotted by the driver, but also the cyclist is also aware of the driver behind them. We've then got the anticipate phase where the driver's anticipating the overtake. They're checking their wing mirrors and they're sort of aware that they could overtake when the cars have gone past because of the dashed line in the middle of the road. And they've got the decision point in grey there, which is it safe to overtake? And then that response, so overtaking, and then determining if they've gone past a cyclist, and then they can pull in, and then they go back to monitoring in the future to see if there's any other future cyclists coming up ahead as well. So that was sort of the operator event sequence diagram, just mapping it out across the different actors to understand who's doing what and where the interactions lay. The second stage then is sort of the resilience aspect of what can go wrong. And this is where we wanted to identify possible errors that can occur. And we applied the Sherpa, the systemic human error reduction and prediction approach, which is a really popular error analysis method, and we like it because it's able to understand the errors, but also can predict and help inform remedial measures or ways to recover from the errors as well. But just to highlight that this does say human error. There's been sort of recent state of science paper in human factors field that says that we should be rejecting human error as a cause of adverse events, and sort of identifying the wider systemic influence of sort of other factors that might relate to error, and not just blaming the individual, particularly when we're talking about these complex socio-technical systems where there's a lot of interacting actors, and quite often just placing the blame on the user. The individual doesn't actually fully understand or take into account all the other aspects of a system which might need to be targeted with remedial measures. So we were aware of that when we were doing this work, which I'll come back to in a second. Sort of process for this Sherpa analysis was task identification. So we had our hierarchical task analysis and the operator event sequence diagrams. And then we needed to identify the errors. So we did this, the Sherpa's got a taxonomy of errors, which is on the right here, which is a list of all possible errors that could go wrong, or things that could happen to result in errors. So we applied this to sort of see against our task where these possible errors might be coming from. Then we looked at doing a probability analysis. So we needed to see how likely these errors were and how critical they might be. So we looked at previous statistics from data sources where they reported incidences and how critical they might be, to sort of get an idea for where these errors might be occurring. And then we did the recovery analysis. So this is where we distinguish between error and failures. So to give you sort of an example here, we have the task of having a bike lane determining space for a cyclist on the road. There might be an information error here. So say the sign's not very clear, the markings might have rubbed off the road. Then there could be an information retrieval error. But this could then be recovered by another event later on in the process, which is the task of the driver seeing the cyclist. So if that means that error has been recovered from, because the cyclist has been detected by the driver anyway, even though there wasn't a sort of signpost to it. But then the driver could also fail to check the roadway for the cyclist. They might not see the cyclist. So this would be a checking error. But that could also be recovered by a future event of the cyclist being made aware of the driver from behind them. So we've got these dashed lines that sort of show the recovery aspect of it. But then if the cyclist is not aware of the driver being behind them and the driver's not aware of the cyclist in front of them, then that's when we get a failure. There's no recovery for that. There's no other sort of future events that could save it. And so we've got this failure here. So we can trace back these errors and these failures to sort of understand the difference between them within this methodology. So the Sherpa had never been applied to the operator event sequence diagram before. So we're getting a picture of how interactions between different actors can then lead to errors and failures within a system. It's just kind of the value of this paper. And then what we can do is try and identify the sort of some frequency counts here. So we had 52 total events and we had 44 errors that were identified. 25 of these were critical, so quite a high criticality, but the sort of quite reflects the sort of risks that's involved in roadways and particularly interactions with vulnerable road users. And 11 of our errors led to failures. So that's a quarter of all errors had failures, which was errors where there was sort of no recovery built in. So some sort of quantification here as well. And then the next phase is the third phase, which is how can it be improved, which is where we start to look at these automation sort of remedies or inputs. And the key way we look at that within human factors is like 4 key areas. So we have the organizational remedies, which is things that we can target in terms of the infrastructure. So maybe improving infrastructure with segregation. Also more connected roadways. So this sort of more communication, vehicle to vehicle, vehicle to bike, vehicle to infrastructure communications. Equipment itself, so obviously automation detection sensors being built into vehicles, as well as external HMI. So this is HMI that's being maybe put on the outside of a vehicle or on a cyclist, so that they can be aware of the communication between the two of them. And this is something that we're kind of following up on in future work. Siobhan's doing some focus groups with drivers and cyclists to sort of understand this a bit more, this eHMI and its value. Also procedural, so looking at overtaking distances, if we need to build these into future automated vehicles, and training as well. So do cyclists and drivers need some sort of training in a future automated situation to sort of identify when they might need to be aware of each other. So what we then did with these remedial measures was sort of build them into this future operator event sequence diagram, so we can add on extra columns under the vehicle. We've got sort of extra swim lanes, so there's the HMI, there's the physical controls of the vehicle communication systems, the sensors, and then the other elements sort of stay the same, but there was more events here. So you can see that the road infrastructure, so the boxes that are dashed are sort of the new events, and the double arrows are the new interactions. So the road infrastructure, you could have segregated lanes, then that sort of links into vehicle sensors being able to detect cycle lanes, and also the vehicle having physical control to then respond to those cycle lanes, the HMI displaying possible upcoming issues or cyclists as it comes along. So what we could do there is sort of map out these additional interactions within the system to sort of get a clear idea of how automation can be integrated to build in more resilience. And just taking it back to these kind of quantitative aspect of it, we can compare a manual and an automated scenario. So we did the error analysis for that operator event sequence diagram as well. And sort of the figures show here. So in the automated scenario, there was more events, it's more complex, which so we'd expect to have more events. And there were more possible errors that were occurring in the more automated one as well. But the criticality of those errors wasn't really significantly any different. There was sort of still a number of critical errors. It was slightly reduced. But importantly, there was a lot fewer failures that were occurring in the automated scenario, and this was because there was more resilience built in with the more backup support from different actors and different tasks within the system. So when automation is operating well, which was what we assumed in this analysis here, then the opportunity for failures actually reduces when you look at it from this sort of system interaction point. So that was sort of the main output of that work. The second phase of our work we've been building on is cognitive work analysis, which is a very popular method in human factors, and it's a really useful framework to apply to sort of new and developing systems. It's essentially a framework, it's a toolkit with lots of different methodologies that you can apply within it. And it's really useful at looking at the boundaries of systems and understanding how a system could perform, not necessarily how it does at the moment or how it should perform. So sort of able to look at things from more of a sort of blue sky perspective and understand how you sort of could design a system to work if you sort of took down the boundaries a bit more. So there's sort of 5 key phases or methodologies, and you don't have to apply all of these. You sort of select the ones that you think might be more appropriate to the sort of the domain that you're working in and the problems that you're trying to solve. So for this work, we applied the work domain analysis and the strategy analysis as the 2 key methods, which I'll go into now. So work domain analysis is the first and usually the most popularly used sort of tool or method within the cognitive work analysis. And this is because it provides quite a good picture of a system and it decomposes it into a sort of hierarchy. So the main method is the abstraction hierarchy, which has got 5 different levels. And the benefit of this is it sort of takes a system from the physical objects, which is that very bottom level of the hierarchy. So you get all the physical components of the system, and then you map them out onto the processes that those objects are conducting. And then you look at those processes and related to the higher level functions. And then you're able to look at the values and priorities of a system and try and understand how these objects within it are related to that sort of the values of a system. So you can design the system to meet the values that you want it to be showing. So just to sort of illustrate that in what the abstraction hierarchy ends up looking like. So you can link up these different levels, and usually the process goes from how does it do this, what is it doing, and why. And I think the why is the really important element of that, which sometimes gets missed out. So when you're thinking about designing a system and looking at designing the individual objects within it, you can then link it up to say, why does it need to do it in this way, and sort of question the design of a system in that way. So we did this for the safely overtaking a cyclist scenario. So we have the functional purpose at the top, which is safely overtaking the cyclist. And then we've got the different values and priorities within that. So giving appropriate road space to other road users, not endangering other road users, and so on and so forth. And then sort of taking that down. So We can look at the different links between them, and it's not really, these links aren't meant to be visible. It's the process of actually linking them up and developing this abstraction hierarchy, which is the real value, and sort of understanding a system in this sort of decomposed way. But just to give some examples, so the value of giving appropriate road space to other road users links down to sort of purposes of keeping the bicycle to the left side of the road and the driver establishing a position behind the cyclist. And these are sort of composed of key tasks, which are lateral control of the bicycle, lateral control of the vehicle, and then the physical objects that relate to that are obviously the bicycle, the cyclist, the driver, the vehicle, but also the steering wheel, possible road markings. So just sort of to give a little bit of an example of how that abstraction boils down. And so then what we wanted to do was sort of look at how these different abstractions and the hierarchy within it relate to possible strategies. So the strategy analysis is another phase of the cognitive work analysis, and it looks at different ways that tasks can be performed, and how different tasks might be achieved, looking at different strategies within sort of the actors and elements within a system, and how the same task might be conducted in different ways. And obviously this is really important when looking at resilience, to understand how a system might be able to perform differently under different demands or under different pressures, or when things go wrong. And there's been a sort of development within this, which is the strategy analysis diagram, which was developed by Parnell in sort of 10 years ago now. And essentially what they aimed to do was develop more of a framework for the strategy analysis. They wanted to understand how you can capture positive performance variability as well as negative, because quite often in human factors we're sort of focused on that human error or looking for negative performance variability, but it's also useful to capture that positive variability when it occurs as well. So they developed this strategy analysis diagram, which gives more structure, and it enables the values and priorities of a system to be able to incorporate it in the different strategies in ways that the performance of a system, a way that systems can perform. And we thought it'd be really useful to apply this because in the work that's being done within the Reason Project, looking at SLEEK norms, so social, legal, empathy, ethical and cultural norms. Obviously these are kind of key values of a system, and so we thought it'd be quite a useful way of trying to integrate these more within the strategies that systems perform, and sort of relating that back to our work. So the strategy analysis diagram essentially builds on that abstraction hierarchy that I presented before by adding in additional levels. So at the bottom level, you've got actionable verbs, which are the sort of actions into the different strategies, so the different actions that can be performed on the physical objects on the level above. And then you also have the additional level of criteria. So this is where you identify key criteria that will determine if strategies are successful or not. And you can link these criteria to the values and the priorities. And then I've also added in where the SLEEK norms might sit within this as well. So obviously the different values and priorities linked to the different potential SLEEK norms. So we just thought it was quite a good way of encapsulating some of this work that's been done on the SLEEK norms by the people in the Reason Project, particularly Bev and Sinem at the University of York. And so this is sort of what it looks like with the verbs at the bottom and the criteria fitting in here. And then again, we went back to the verbs being these resilience pillars. So we're looking for resilient strategies. So we could build these resilience pillars back in from the bottom to sort of understand how these different strategies related to monitoring, detecting, anticipating, responding and learning might look throughout the system. And then sort of SLEEK norms fitting in there. And this is essentially sort of what it looks like in terms of the transport scenario. So we've got these different criteria. So is it a competent cyclist? Are there upcoming vehicles being present? Is there a cycle lane present? And so what we could do is sort of look at the strategies through the diagram. And it's kind of complex to represent in visual form. So apologies, but I put it in table form. But essentially what we can do, and I just illustrate this with an example, is we can take each of the functions of a system and look at the different strategies that can be achieved to determine, so sort of achieve that function. So the function of determining the time to overtake, there's different ways that you can determine the time to overtake, and there's going to be different values that are going to inform that decision as well. And this analysis was actually informed by some focus groups that were done as part of that previous study by Katie, the Critical Project, which is looking at the training program for drivers and cyclists. But we had this qualitative data from drivers and cyclists interacting and talking about how they might go about an overtake scenario. So we had that data to illustrate and use for us this strategy analysis. So we've got the determining time to overtake. So the users in the focus group said that actually they might look to the cyclists themselves to see how competent they were, and that would inform them of how long it would need to overtake. So if you've got a family traveling with small children, you're going to have to allow for a longer time and give them a bit more space than maybe if you had a competent cyclist who looked like someone who cycled quite a lot. So one of the strategies here would be that you're monitoring, the driver's monitoring the bicycle and the cyclist. They're doing the hazard perception, and from this they're going through the criteria of determining, are they a competent cyclist. They're informed by the value of giving appropriate road space to other road users. The sleek norm here, maximising good outcomes, not wanting to sort of get into a collision, which then informs that determining the time to overtake. And then you can also look at other related functions to it as well, but I won't focus too much on that. Another strategy, sort of more from the cyclist perspective, this is where they're sort of looking at the cyclists' sort of line of travel, and they talked about how their positioning on the road would be influenced quite a lot by potential drain covers or ruts, potholes, and the cyclists being quite aware of these, especially if they travel there quite a lot, or they might be more cautious if it's an unfamiliar environment. So they're going to be monitoring the road surfaces, making sure that there's smooth travel. Their criteria here is there potholes or is there hazards? And then being aware of these environmental factors. They're also going to be monitoring for information for other road users. Is there a cycle lane present, which is going to inform their positioning on the road as well. So it's just getting these different strategies in place which is informed by this secondary data analysis to sort of build a bigger picture about what these strategies are and how they might relate to wider norms on the road. So that's sort of some of the work on the transport scenario. The next phase was looking to apply some of this to another scenario within the Reason project. So we've been doing some work on the assistive care dressing scenario, which is sort of a robot that can assist you around the home. And this has been studied and worked on by Sinem at the University of York, and also Bev and Raju and the team there, looking at lots of different elements of the scenario, but we wanted to see if we could apply some of the work we've done in the transport scenario, some of the modelling work that I just described, to this sort of scenario. And we did this in a, it's just been accepted for publication, but in the symposium, the TAS symposium, which is going to be in Edinburgh in July, we've written a paper called Resilient Strategies for Socially Compliant Autonomous Assistive Dressing Robots. And essentially this came about by discussions that me and Sinem had about how maybe we can use some of these strategies and strategy analysis to inform the requirements for resilient autonomous systems, and sort of building them and embedding them into the language that's being written. And so how can we translate some of this human factors work into a more structured language, and how can it sort of go and sort of inform some of these sleep requirements and things like that. And so the objectives we had was generating useful information about systems capability and its environment. So we did this abstraction hierarchy to sort of build a bit more information about the system, identifying possible strategies and what that human robot interaction might look like, and then using this to inform and develop some sleep language. And essentially what this sort of aimed to do was provide a bit more explainability and traceability into the system. And then the output and sort of the useful element of it is sort of providing a feedback loop for stakeholders as well. So how can the stakeholder be informed in this decision, informed in this design process? As at the beginning about wanting to involve users throughout. So it's really important that development of this language is sort of informed by stakeholders as well as by sort of us as researchers. So we worked on this scenario. We based it loosely around the work that had been done at the University of Sheffield on a robot assisted sort of, it's a robot arm that can help you get dressed. It can put sort of, it's quite rudimentary at the moment, so we're kind of thinking about it's not exactly the components and the capabilities that has at the moment. So we had a bit of creativity involved in the actual development of it because it's still very in the early stages. But the main purpose of this work was to look at the methodologies and kind of come up with a framework where we could look at these interactions between us as human factors and the more computer sciencey elements of it as well. So we had the scenario of this robot assisting with putting on a hospital gown in a hospital, and then the scenario from a resilience perspective looking at responding to if the user had fallen off the chair and what the robot might be doing in this scenario. So where we thought this might sort of the purpose of this work and how to sort of present it. We had this strategy analysis diagram, and sort of this is just a high level overview of it, but we thought that the criteria element might be a key area in which we can then overlap and integrate in this sort of formalized language that's being developed by Sinem. And I'm not a computer scientist, so excuse me if I'm not really referring to this correctly. But from our side, from a human factors perspective, we can identify these key criteria, which is going to be what the robot's also going to be needing to do when it's sort of acting more autonomously, and then use this criteria and the information that we have in the abstraction hierarchy to then give more of a framework to this language, and give some sort of context to what this system is actually doing at these key criteria sort of pinch points. So we did an abstraction hierarchy of the dressing scenario. You can see the functional purpose of appropriate dressing assistance, and then we tried to populate it as best we could, and looking at these different interactions and the different ways that the human and the robot might be interacting, and sort of getting the physical components, although it's by no means complete. We did it as sort of a process of being able to sort of proof of concept, and we were using sort of a paper from the University of Sheffield as the basis for this work to sort of get it as accurate as possible, but it's not by any means absolutely full as it is at the moment. It's more sort of just for an example. And then we could sort of develop from this, put in the strategy. So the verbs, again, we use the sort of resilience verbs, and then we identify some key criteria. So some of the criteria might be, is the room temperature adequate for this kind of dressing? Is there adequate privacy? Is the body mapping that's going on? So they can do some body mapping, physiology mapping of the person's body. Is that accurate? So some of these key criteria. And then we wanted to relate that back to this scenario of the user falling off the chair. So we had some of the language that had been written already, which is sort of defining these key events. So one of the events is the user's fallen, another event is support called, and then we also have the measures. And so what we wanted to do is sort of identify within these strategies, how is it that these strategies might then relate to these rules. And so we identified the sort of criteria that we had is the user in the correct position. And so if we identify that criteria, we can then look at the different strategies that the system goes through in order to determine that the user's in the correct position. So we've got all these different strategies that then relate to the physical objects and the processes that these objects do to determine if the user's in the correct position. So these are kind of a starting point to understand where the robot and where the automated system is going to need to look for these different individual elements of the system. And then we also have a related criteria, which is the user's not distressed. So there's, I think, related to this, we have the criteria of making sure the user's not distressed, and if they are distressed, what needs to be done about it. The other event is support called. So we have the criteria here of backup assistance might be needed, and the different strategies that are put in place in order to determine if backup assistance is needed and how that should be operationalized. And then also the emergency response. So if it's determined that it is very critical, the user's in quite a lot of distress, what the emergency response might be. So we're sort of building in our strategy analysis and relating it to these rules that have been written to sort of build a bigger picture of the system. And then what we could do is get that stakeholder input. So we could take each of these criteria and say, okay, well, how do we know if this criteria has been met or not? And so the output of this paper was providing some key questions that we might need to then go back to stakeholders with. So how do you determine currently if the user sat in the correct position? What level of movement would you expect? And also from patients as well, what's a comfortable position for you? What kind of factors might be influencing if you might fall or not? And then also similar questions relating distressed, if backup assistance is needed, emergency response. So what this analysis and this process did was sort of build a bigger picture and a bigger framework for us then to go back to the stakeholders with potential questions that can then be built in and included in the sort of future iterations of this system. So just sort of to finish off then some future work. So we're continuing our work on this assistive care dressing scenario, working with Bev, who was also given one of these talks, about normative conflicts. So we're looking at how maybe working together we can look at resolving some conflicts that might arise between different normative principles. So for instance, in dressing scenarios, how do you balance ethics with privacy concerns, and mapping out decision makings to understand how these conflicts might be resolved. And so sort of working very interdisciplinary on this, and it's been quite interesting to sort of just trying to get the right language in place and understand how our different approaches can be used together to get some sort of meaningful outputs. And ultimately, I think what we've decided is that sort of working together, we can get a sort of framework for stakeholders and how they start to include them in the decision-making process and into the development of future rules as well. So the method that we're going to be doing is sort of the next phase of the cognitive work analysis, which is a decision ladder analysis. So we can use the work that we've already done and build on this. And a decision ladder is essentially not exactly the same as a decision tree, but what it can do is account for a little bit more of sort of more naturalistic decision and sort of the wider context and environment that decisions are made in. So we've got this initial activation point of a decision. So what we can sort of identify what it is that determines a decision needs to be made. And then the information that is then needed to inform the sort of diagnosis of that system. So it sort of builds up from the bottom left up to the top and then down again. So once you've got the diagnosis, you can have potential consequences and then a list of different options that you might go through before you sort of select the option that you want. And then you go back down. So once you've chosen that option, you can then determine what the target state needs to be and the different tasks that then need to be actioned within that as well. So hopefully this is kind of a good process and toolkit for enabling us to sort of think about those different normative conflicts that might arise. And then just finally, we're also doing some future work on our automated transport scenario. This is some work that Siobhan's leading, doing some data collection. And so we're sort of going back to that external HMI and trying to identify if and what that might look like, and if that's actually going to be a useful thing to progress. So we're doing some work on what current overtaking experiences are like. So having focus groups with drivers and with cyclists together, trying to sort of facilitate that conversation, understand what their decision-making processes currently are, what trust they might have, and then also talking about what that might look like in an automated system and what their sort of acceptance might be of external HMIs, and what they might want that to look like or not want that to look like. So that's just some sort of future direction for data collection with users, and hopefully in the future maybe we can do that with the dressing scenario as well. But yeah, that's all from me. So thank you for listening.
Thank you very much, Katie. So I think we can have the questions now. Is there any question? I see a question from Chiara on chat, so let me read it. So Chiara says, thanks for the talk, very interesting. How do you see we can embed the human factors considerations during the design of the autonomous systems?
Yeah, so I think that comes from making sure that human factors is considered early on in the design process, and a lot of other work that we've been involved in, quite often it comes in a bit like too little too late. So the processes that I've outlined, particularly that sort of first block, that process going through is sort of, it's iterative, and it's making sure that we engage end users and also stakeholders as well within that process, which is what we're trying to do with that dressing scenario. So we've done the modelling work, and then once we've done that initial modelling work, it's going out and talking to key stakeholders, users, and also sort of professionals to get their inputs before you then do another iterative cycle of then remodelling things. So a lot of the work is talking to users and integrating it in sort of iteratively. But also within that, it's kind of key to identify who those key stakeholders are, and who you need to be talking to when.
Yeah, thank you. There is one question from Christopher. Please.
Thank you, Sinem, and Katie, thank you very much for the really interesting presentation. A lot of the methodologies were quite new to me, so apologies for either a potentially naive question or maybe just missing this. And I've also got a quick comment after my question. Early on, you said that when discussing the Sherpa methodology, that one of the limitations that have been present in the literature is the focus on human users, and that especially with socio-technical systems, there are many further components that kind of complicate the sort of the narrow focus on sort of human users as failure modes. Can I just ask you just to expand a little bit on this and just to give you some context? I work at the Turing Institute, and a lot of the work that we're doing at the moment is focused on data-driven technologies and understanding what is often sometimes a socio-technical life cycle of design, development, deployment, where, for instance, some of the problems could arise in data collection or the way in which the training of models goes through, as well as the way that they're deployed, implemented within different systems, and then, of course, failures in their use. And I just wanted to know whether or not the sort of limitations you were alluding to were were sort of similarly mappable onto something like that very elongated project lifecycle, or if there's anything else maybe you can expand on. And I'll pause there before I maybe just share a quick comment afterwards.
Yeah, so I guess the human error element was the fact that traditionally when something's gone wrong, and it's generally in sort of accident analysis, it sort of places the blame on the human for maybe not following training protocols, rather than looking at the fact that those training protocols may not have been designed effectively and have let that come to be. So it's looking at it sort of from a more systemic perspective. So in terms of looking at, data collection sounds like a great way to sort of look at that from, are you collecting the right data on a system, which is more systemic than just sort of looking at the end user. So I don't know if that was your question. Or...
There's also more just in terms of understanding, say, like the resilience of a data-driven technology or some system that maybe utilizes machine learning, where the actual way in which the capability of that model to actually serve as an appropriate kind of basis or component of a larger system is less about how human users interact with the system, but more about whether or not the model's been trained effectively on an appropriate data set, or whether the data is truly representative of the different environments in which that system should be operating. And the question was more just, was the limitation you alluded to early on sort of driving at those kind of concerns? And if so, are there other concerns that go beyond that just initial kind of data representativeness aspect?
Yeah, definitely. So it's sort of, in terms of automated features, how those are designed and how they're developed, they're coming from the group of designers that have designed them. Do they have any other? And that's why we're really keen to sort of get the stakeholders involved and understand from lots of different perspectives how they are going to be utilizing, or the different environments that they're going to be utilized in. So it's capturing that big picture, and also obviously like the regulations of systems in the future is going to be really key to that as well, because so that's the element that's kind of missing a lot of the time.
So then, do you mind if I just have a very quick comment before I put my hand down? I've seen that. The comment, Katie, was just that, so last year I was PI for a TAS Hub funded project that we did a lot of work with University of York's TASNet on, focusing also on normative considerations of data-driven technologies. But we were less focused on like the analysis of the potential conflicts between normative values, like the ones you alluded to, and more about how you provide assurance using argument-based assurance as a methodology, which also links to York. How you provide or communicate assurance that those trade-offs, those conflicts have been dealt with. So the comment is just, if this is something you're continuing to look into, we're very interested in having a further conversation about that beyond the scope of this workshop, because I'm assuming the two sort of approaches would be quite complementary, whereas you're trying to analyze, for instance, where those kind of conflicts arise. That could be a very good sort of evidence base for the type of assurance techniques we're considering. And we just started a new project with York. So if you're amenable to it, I'll happily send you an email and follow up on that point.
Yeah, definitely. I think that was in the sort of work that we've been, group that we've been discussing, is that next step is what we're going to be looking at, and working with Ibrahim, the University of York. Yeah, so he's the co-investigator on this project that's just started. Yeah. So he's involved and hopefully looking at that. So yeah, definitely be interested in.
I'll send you an email. Thank you.
Right.
Thank you, Christopher. So we have a question from Callum.
Hi. Yes, no, that was a really interesting talk. Thank you very much. So I'm also not very well versed in this field at all, or the sort of methodologies that you were applying. So this could be a very naive, ignorant question from me. And I'm not quite sure on how to word it. So apologies in advance. So from what I've kind of seemed to understand from the autonomy systems that kind of been described here as case studies and examples, they seem to me at least to be quite well grounded in the sort of processes that you would expect from them that could be tracked. So for example, in the last one, in the future work, for example, there is like, you know, DVLA processes, guidebooks on how overtaking should occur, you know, to be safe, legal, and all of that. But what about autonomous systems where it's perhaps less certain when, you know, exactly how it should form? So for example, I'm thinking of maybe like swarm systems where they rely a lot on self-organization. So even though you know the vague process of it, the actual final outcome of it is, you know, can be quite chaotic, I suppose, even though they have got this self-organized behavior to them. And then when you integrate human into that, being able to really capture that. And the only sort of other real domain I can think of where maybe the process is not fully well grounded is the maybe like emotional robotics, this idea of this for entertainment purposes, you know, they interact with the user and try to reciprocate and get them to feel good, happy, sad, I don't know. Again, like I said, I'm not quite sure how to word it, but I was wondering if there's been consideration to more of these sort of domains that aren't well formulated, I suppose, currently.
Yeah, no, so it's a good question. And I think that's definitely where human factors is trying to catch up a bit more and understand these systems where they look like a bit less physically developed, because traditionally we do a lot more sort of transport and military type stuff. But I think that's kind of the point I was also trying to get across in that cognitive work analysis methodology, because it's unbounded. So what it does is try and think of, it aims to look at future systems. So it gives you a toolkit to start to look at these kind of things. And that's sort of what I was coming across with sort of saying that you've got those values and priorities of a system in a system such as you've described, and then trying to link that down to possibly more physical objects, which is a difficult process. But the methodology is there to sort of help you try and structure that a bit more. And actually that's kind of what we've found when we've been trying to apply to this assisted dressing scenario, where we didn't have so many tangible or as tangible sort of elements to it as we did with this transport scenario, which actually sort of generated more questions than it answered in a lot of ways. But that was kind of useful in itself, because we started to think, okay, well, how will that interaction look like? Will there be voice interactions? Will there be the need for this? So that's sort of the methodologies are a framework to start those conversations, which is often really hard to do, especially working interdisciplinary. So I think we found that this is kind of the tools that we have are actually really useful to start the discussions and start to think about these questions a bit more rather than solve them. So I think, yeah, that would be what I would say on that point, if that was what you were intending.
No, absolutely. Yeah. And I suspected that I might have missed something. So I guess if I'm allowed to a follow-up question on this.
Yes, please go ahead.
So as you say, though, you start off with this sort of general, so for example, the assisted dressing, and as you put it, ask, you know, more questions than answered and all that. Is there a slight concern, I suppose, that you end up taking this sort of, I don't know, a problem or an application and making it too restrictive and constrained so that it is able to take into all the accounts of the human factors elements, and you do remove, I guess, some of the flexibility from the application and system and give it that versatility? Or have you not really found this to be the case so far?
I guess we haven't got that far down the road, but I definitely think maybe from being a human factors engineer, we're definitely more on the side of the human. And I think what we find a lot of the time is that maybe the human should be more involved than what autonomous system designers or people that way. So it's definitely a balance that we would, why the collaboration is needed there between different people from different perspectives, I think. So yeah.
Thank you.
Thank you. I have maybe one question regarding the first part of your presentation. You were introducing your method about the failures and recoveries for resilience autonomous systems. Can you say a bit more about this recovery durations? Because, I mean, the performance of this recovery in real practice, how does it work? Is it really effective?
So yeah, I guess that was kind of making the distinction between people just sort of blaming an error, and then also when you can look at it from sort of more systemic sort of factors that can come into play. So I guess the purpose of it was kind of illustrative in showing the differences, which might be just like, oh, one thing's gone wrong, but actually the system itself can build in that resilience to a certain extent. So it's a method that we've kind of come up with to look at errors in terms of being a bit more interactional between different elements of a system, and it'd be really interesting to sort of explore that a bit more in maybe a more or less constrained environment as well. That's sort of just been asked that question. So yeah, I think it's not always obvious maybe when you think about it in day-to-day life, but when we go into it and sort of explore this, what we like to do in human factors is very much break things down into all the individual elements and items, as sort of I've illustrated. It becomes clear that you can look at the sort of interaction between different systems elements a lot more in a lot more detail.
Okay, thank you. I have another question regarding this abstraction hierarchy diagrams. So did you observe some kind of levels to make it abstract? Like, I mean, the granularity of this abstraction, does it affect the analysis of these diagrams or the explainability of these diagrams? So, I mean, it seems like when we have more information, we should have more explainability, but is it getting difficult to analyze these diagrams?
They definitely can become very large when we look at very large systems. I think you have to make a lot of assumptions from the outset about how much detail you're going to go into. And I think in terms of future systems, there's sort of a caveat that has to be said within that. But it definitely, you can get very granular with current systems. I've just done one sort of looking at e-scooters and looking at sort of recommendations for future e-scooter systems. And we got really granular, sort of right down to sort of the mechanisms within the motors of the electric systems, all the way up to sort of the values of the needing to sort of have more sustainable travel and things like that. So there is, depending on the sort of analysis that you want to do, you can go into lots of sort of different levels of granularity.
Mm-hmm. Okay. Yeah, that's interesting. Thank you very much, Katie. I think, yeah, we're, I think it's time to finish here.
Great.
So thank you very much. I think for the next seminars, you will get emails from Hayley. And thank you everyone for attending this seminar. See you next time.
Thank you.
See you. Bye.
Bye.